Sharks are older than trees, older than Saturn's rings, according to some recent planetary research. They were already swimming through Earth's oceans before the first dinosaur ever existed, and they were still swimming through those same oceans long after every dinosaur was gone. Sharks have survived all 5 of Earth's major mass extinctions, the same catastrophic events that wiped out the vast majority of species alive at the time, again and again, for roughly 400 million years. That sounds like a story about an invincible survivor. It isn't, quite. And the real reason sharks made it through, along with the one time they very nearly didn't, tells you something specific about what resilience actually requires. Start with the scale of what sharks have lived through. The Ordovician Silurian extinction, roughly 443 million years ago. The late Devonian extinction, around 375 million years ago. The Permian-Triassic extinction, close to 252 million years ago, so severe that paleontologists sometimes call it simply the Great Dying, wiping out somewhere around 90 to 96% of all marine species on the planet. The Triassic-Jurassic extinction, roughly 201 million years ago, and the Cretaceous-Paleogene extinction, 66 million years ago, the asteroid impact that ended the reign of non-avian dinosaurs entirely. 5 separate, planet-altering catastrophes. 5 times, sharks kept swimming while huge swaths of life around them simply vanished. So what specifically let a cartilaginous fish outlast events that erased entire branches of the tree of life? Part of the answer is architectural, and it starts with something sharks don't have that most large animals do: bone. A shark's skeleton is made almost entirely of cartilage, the same flexible material forming the structure of your own ears and the tip of your nose, rather than the calcified bone making up your skeleton. Cartilage is lighter, requires less metabolic investment to build and maintain, and gives a shark's body a kind of structural flexibility that a rigid bony skeleton doesn't offer. In the aftermath of a mass extinction, when food sources collapse and ecosystems become unpredictable and sparse, an animal that costs less to build and maintain has a real advantage simply by needing less to survive. That cartilage skeleton comes with an odd side effect worth mentioning because it explains something about how we even know this history at all. Cartilage decomposes far more readily than bone, meaning complete shark skeletons almost never survive as fossils. What paleontologists find instead, overwhelmingly, are shark teeth, and to a lesser extent, tiny tooth-like scales covering their skin, called dermal denticles. Sharks continuously grow and shed teeth throughout their entire lives, some species producing thousands of individual teeth across a lifetime, and it's largely from this scattered, relentless dental record, rather than complete skeletons, that scientists have reconstructed 400 million years of shark history at all. Beyond the skeleton, sharks carry a body plan that's remarkably generalist. Paleontological research on elasmobranch diversification, including work published by researchers Guillaume Guignot and Fabien Cavin, examining how shark and ray lineages responded to the Permian-Triassic extinction specifically, found that while some shark groups did go extinct during that catastrophic period, others weathered it by being flexible enough in diet, habitat, and hunting strategy to adjust as marine ecosystems collapsed and reorganized around them. Sharks, broadly, aren't hyper-specialized for one narrow food source or one specific habitat the way many extinct marine reptiles were. That flexibility across diet, depth, temperature tolerance, and geographic range meant that even when specific shark species or lineages vanished during a given extinction event, the broader shark lineage as a whole nearly always had some population somewhere positioned to make it through. Add to that a genuinely wide geographic distribution across essentially every ocean on the planet, and you get a lineage that's structurally difficult to wipe out completely, because no single localized catastrophe, no matter how severe, was ever likely to reach every population of sharks simultaneously. This is where the story could end, a tidy account of a resilient, adaptable survivor built correctly from the start. Except sharks nearly didn't make it through something else entirely, something far more recent and far stranger, because almost nobody knew it happened until 2019. Researchers Elizabeth Seibert and Leah Rubin, studying deep-sea sediment cores containing millions of years of accumulated microscopic shark scales, published findings in the journal Science, documenting something previously unknown to paleontology entirely. A massive, sudden collapse in shark populations roughly 19 million years ago during the Miocene epoch. Their analysis of these tiny fossilized denticles, painstakingly counted across sediment layers spanning millions of years, showed shark abundance and diversity dropping by roughly 90% in what appears to be a geologically sudden event. Not a slow decline stretched across eons, but something close to a rapid collapse. Here's the detail that should genuinely unsettle you. This wasn't one of the 5 recognized mass extinctions. It doesn't appear in any existing extinction record. No widely known catastrophic trigger, no asteroid, no supervolcano, no obvious climate collapse has been definitively linked to it. Seibert and Rubin's research essentially uncovered an entirely unknown, previously undocumented near catastrophe for one of the most resilient lineages in the history of life on Earth, sitting quietly in sediment cores, undiscovered for millions of years, until someone finally counted the right microscopic fossils carefully enough to notice the drop. Which raises an uncomfortable question. If sharks survived 5 confirmed, well-documented, planet-altering mass extinctions through structural flexibility and geographic spread, how did they nearly get wiped out by something so severe it erased 90% of their population, and yet so quiet that science didn't even know to look for it until a few years ago? The honest answer is that resilience built for one category of threat isn't automatically resilience against every category of threat. Sharks are extraordinarily well adapted to survive slow-building environmental pressure, gradual climate shifts, ecosystem reorganization following an asteroid impact, the kind of change that unfolds over thousands or millions of years, giving a generalist body plan time to find its footing in a changing world. What that same resilience doesn't necessarily protect against is something sudden, poorly understood, and invisible to the systems built to notice large, obvious threats. The 5 mass extinctions left unmistakable geological fingerprints, iridium layers, ash deposits, sudden and dramatic shifts in the fossil record that scientists could identify and study for over a century. The Miocene shark collapse left almost nothing except a barely perceptible drop in microscopic scale abundance, buried in sediment cores. Nobody thought to examine that specifically until very recently. This distinction matters well beyond shark biology. You've probably built your own version of resilience around threats you can clearly see coming, financial setbacks you've weathered before, familiar conflicts you know how to navigate, seasonal changes in your work or your mood that you've learned to anticipate and absorb. That kind of resilience is real, and it's earned, but it's also calibrated specifically to the shape of dangers you've already survived, the ones with a recognizable signature, the ones that leave an obvious mark you can point to afterward. The risks that actually catch people off guard are rarely the ones that resemble anything they've successfully weathered before. They're the quiet ones, the ones that don't announce themselves with a dramatic, identifiable event, the ones that only become visible in hindsight once someone finally goes back and carefully counts what was actually happening the whole time. Sharks are still here. That part of the story is genuinely true and genuinely remarkable. 400 million years of continuity through 5 separate planetary catastrophes is not a small thing to have survived. But the fact that they nearly didn't make it through a 6th event, so recent and so invisible that scientists only found the evidence a few years ago, should complicate any tidy story about invincibility. The lineage that outlasted the asteroid that killed the dinosaurs still had a blind spot severe enough to erase 90% of its population, and it took millions of years and an extraordinarily patient sediment analysis for anyone to even notice it happened. Modern researchers are still working out what actually caused the Miocene collapse, whether it traces back to a shift in ocean productivity, a change in prey availability, or some combination of pressures that hasn't been fully reconstructed yet. Until that answer arrives, the honest version of the shark's survival story isn't simply that they're unstoppable. It's that they're remarkably good at surviving the threats built to look like threats, and, like almost everything else that's ever lived on this planet, still capable of being blindsided by the ones that aren't. Sharks are older than trees, older, by some research, than Saturn's rings, and they swam through 5 mass extinctions that erased the vast majority of life around them each time. They're also, it turns out, survivors of a sixth event nobody knew to look for until a few years ago. A reminder that the resilience built to handle the disasters you can see is never quite the same thing as being safe from the ones you can't.